All right. So today we will complete our study of graph traversals, and last time we studied breadth first search, and we also looked at an example for depth first search. We will go over this in a little bit more detail, and we will see a couple of interesting applications of it. One is how to look at graphs, directed graphs that don't have cycles. We call them directed acyclic graphs, and a very nice application of depth first search for finding components of a directed graph, and we'll explain how we go about this. So this, I was just going over the schedule, and I noticed that there was a mistake in the schedule. So the problem set 4 will be posted today, today. For some reason, it listed problem set 4 as being out beginning of next week. So it will be out today, and it will cover graph traversals. Okay. Also, some of this material we will be covering in more detail than that is what is there in the book. So there will be other references also posted for it. Okay. In terms of grading, midterm grading is going on. We'll probably complete by maybe this Friday, but most likely next Tuesday. Problem set 2 is finished grading. You will soon get your grades. And we are also working on problem set 3. Okay, and I have your quiz 1 grades that I have. Okay, good. And we will go over the midterm questions once the grading is good. So let's look at just review the 2 kinds of traversals that are most depth first search and depth first search. Okay. And both of the idea of breadth first search is you think of exploring vertices and edges. So the role of both of these is to explore the entire graph. And the way breadth first search operates is once it discovers a vertex, it puts it in a queue. So they are visited in the order they are explored in the order they are first discovered. Okay, so you first start from a vertex, look at all of its children, so then you discover the vertex, put it in queue. Then exploring visits. Goes through all edges. Okay. Depth first search. On the other hand, discovers the vertex. When it discovers the vertex, it puts it in a stack, so that the next one to visit is that vertex that you've just discovered. Okay, so when exploring, again, it goes through all of the edges. It goes through one edge at a time. Okay. Okay, so let's let me say a few more things about BFS versus BFS. So if you do undirected graphs, both can be used to find connected components. Okay. When you do undirected graphs, both can be used to find connected components. Okay, again, recall what are connected components. Connected components are pieces of the graph that are such that in any piece, all the vertices have paths between them. Okay, so undirected graphs both can find BFS and DFS can find connected components, and they both take linear time. Okay, maybe I can. It might be easier to see that in the table form. So let's say we write for so this is BFS. The time in both cases is zero and 1. And connected components. In undirected graphs, both of them do that. Okay. How things are, in what order of exploration. BFS uses a queue. Depth of search uses a stack. Okay, to figure out which order you should explore. Shortest paths. Does it find shortest hop paths? This finds BFS is not designed to find shortest hop paths. And other than that, there is some notion of classification of edges. Each of them can be used to classify edges. Okay. Both of them do some kinds of, there is a tree edge. There is a notion of a tree edge. There is a notion of a cross edge. There is a notion of a back edge in DFS, and we will go over all of that. And there is also a notion of a forward edge in DFS that we will go over. Okay, so they both of them can be used to figure out how the graph is sort of differently connected. And this is, by the way, for undirected graph. For directed graph, something different is done, and we'll go over that. Okay. Okay. So let's start by drawing an example, and we will do this example with depth of search. Again, So let me just give an example that we will use as a running example for. So this is 12 vertices, and I'll draw some edges. Okay, so this is the graph, and so let's try to let me present DFS, and I'll present it in some kind of pseudocode as well, and you will see how it forms on this as well. So the way DFS works out, so there is the subroutine called, let's call it DFS explore. Sometimes called DFS visit, and there are different names for it, but basically it starts from a given vertex. So it starts from some vertex R. Let's call that the first node, or let's call it source. So some vertex S, which is the source. And it starts from the source and then goes ahead and visits every vertex that it can reach from the source. Okay. So, and so what you do, we go through, so you mark the vertex that you've just discovered it. Okay. Discovered. And then the next thing you do is you go through every edge of it for edge S V. Okay, for edge S V, you do a DFS explore. If we not already discovered, DFS explore. So you find a neighbor. If the neighbor has already been visited before, you don't visit it again. But if it's not been visited, you go ahead and call DFS. So you immediately put it in a queue. So you keep doing this for so you do this for one edge, and notice that once you do that, that's a new call for DFS explore, and then you might do something there, and then you come back. Once you're done going through all of your edges and everything is done, then you mark the vertex as finished. So this is what I'm meaning as the time at which you discovered. This is the time at which you have finished. Okay? You can keep track of some notion of time and mark these times. Okay, so that's basically DFS explore. Okay. Now, if you're trying to visit the entire graph, the way you write down is you write down the DFS for the entire graph, G, and while there exists a vertex let's call it V, not let's call it S. While there exists some vertex S not discovered yet, if there is a vertex that has not yet been discovered, then you go ahead and explore it. Okay? Yes?
So the first DFS Explorer, right?
Yeah.
That's used to just check, you can use that to check the entire graph, right? Because since you're doing recursion, you're going to keep going.
You could, we will see.
Right.
We'll see, we'll try to run it on that example. It really depends upon the graph.
Right.
If it's an undirected graph and it's connected, then when you start your DFS from any explore from any vertex, it will go ahead and visit the entire graph.
So then let's say this is like the example that you just put up, let's say it's an undirected graph.
If it was undirected, there were no directions in these edges,
Yeah,
then no matter where you begin from,
right.
you will visit the entire graph by the time you're done.
So in the way that you've written the algorithm, I think you said you keep like a set, but when you're doing recursion, wouldn't your set get overwritten at each recursive step? Like
Well,
how are you keeping track?
When I said we keep a stack, for example, right?
Okay.
Yeah. So you're right. So it's not really, we are not going to maintain a stack.
Right.
It is implicitly being maintained.
Okay. So
The reason it's implicitly being maintained is the following: that as soon as you see a vertex that's not discovered, you immediately explore it.
So then, let's say we go to like B, right? B has this like loop that goes back and forth.
Well, so let's say you were to do, this was not connected, so it's not directed.
Right.
If you start from B, you will pick an edge around B. It might be A, so you'll go to A.
Right.
You will call DFS Explorer on A. It will have nowhere to go,
Right.
so it will return. So it'll come back here.
Right.
Then you'll pick edge E,
Right.
let's say. Then you will do a DFS Explorer on E, which might do a DFS Explorer on G.
Right. So my problem is, since we're not like when we do DFS, you're maintaining like this array that you can check.
Correct.
With this, we're not maintaining. You were saying implicitly, but like, how are we actually maintaining it? Because if we can go back to B.
Good.
That's
Very good. Very good. Very good. Okay. So that's all written implicitly in this statements like B not discovered.
Oh,
So imagine there is an array that says discovered.
Okay.
It keeps track of which vertices have been discovered, have not been discovered. Okay. And I've written it as a recursive procedure. If you want, you can avoid writing the recursive procedure the other way. Okay. Good question. Yeah. Yes.
So, didn't the recursive procedure work as a stack itself?
Yeah.
That you go through all the each and every step and
Yes.
you go back?
Yes. So this will call this, will call this, will call this, will call. Actually, let's do it in the directed graph. It will be much cleaner when we go. Yeah, we'll go through this. Okay. Okay. So we're going to try to go through this, and I'm going to mark the discovered and finished times. Sometimes these times are referred as explore and post times, post and pre times. So there are lots of names for this. I'm going to use discovered and finished, but there are different names that are used for this. Okay. And sometimes instead of explore, it's visit. Okay, so you don't really avoid it. So the main idea is fairly conceptually very clear. Okay, so let's run this. We're going to do DFS G. Okay, when I say G here, by the way, it's the graph. It's not this vertex G. chain diagram. Okay. Chain diagram. Good. So let's start. So let's pick a vertex on which we're going to run. Okay. So initially, so we will have an array called discovered, and we'll also have an array called finished. Okay? Initially, both the lists are, and imagine we also have this array called not discovered. This keeps track of all the vertices that have not yet been discovered. Okay? And think of it as a linked list, an array, it doesn't matter. A linked list will be simple enough to keep with pointers if needed. So I'm not going to go into the nitty-gritty details of the data structures, but so initially all the vertices are sitting here. Or in the not discovered set. Okay? Now what happens? We are calling the DFS in the graph, so there is the loop. While there exists a vertex not yet discovered, so we look in the list. Is there a vertex that is not yet discovered? Yes. We pick any vertex that we want. It doesn't matter. So the one thing you immediately observe is that DFS can run in many different ways. There is no, the way I've described it, there is no single DFS run. Okay. And there is no reason to fix a particular DFS order. Of course, the algorithm will pick a certain order based on how you describe it. But let's pick anything. So, which vertex do you want to start from? B. Okay. D? B. D. B? Okay, let's do something. Let's say F. Okay? Let's start from F. So, what do? So, we call DFS explore on F. Okay? Good. So, we are going to keep track of this time. So, we run DFS explore on F. That means F will be taken out from here, and now it's discovered, and we will mark, I'm keeping track of this time, at time 0 it is discovered. Okay? Then we go through all the edges out of F, so there is only one edge out of F. S is F, right? So there is only one edge out of F, and that's this edge. Whenever I see an edge leading to a vertex for the very first time, I mark that edge as a special edge. Okay? So one way to do that is if V is not yet discovered, then we will say the parent of V is S. Okay? Because this is the first time I'm discovering this vertex. That's the. And now what do? We call DFS explore on H. So it goes back. And we mark H as discovered. So H comes out of this and goes here. Okay? From H we then come back. We mark H as discovered. For each edge going out of H, there is only one edge going out of H, which is K. That we check whether it's not discovered. So K is not yet discovered. So we mark K as we have an edge between H and K, so we mark that edge separately they have written, and you put K into discovered set, and you go through all the edges out of K. There's only one edge, so you do the same thing. 3, L. Okay? Then what do? You have again only one edge. 4, you go through J, then you have one edge going to I, I is not yet discovered. So that. Then you have one edge going to G. G has not yet been discovered. So mark that. Okay. So far so good. Okay. So now we are calling. So notice that this is the stack. We have the stack calls. Series of stack calls have happened so far. What is the top of the stack? G. What is the bottom of the stack? F. Okay. So now we are calling DFS explore on G. Okay, so we mark G as discovered. Then we go through all the edges of the G. How many edges does G have? 2. So first edge is, let's pick J. Then we check, has J been discovered already? Aha, J has been discovered. Okay. So if we find that J has already been discovered, then we mark this edge differently. Okay, this is a different kind of an edge. Okay. And this edge, okay, so let me mark that as for now this is a dotted one. Similarly, then we look at H. Has H been discovered? Yes. So we again mark that edge differently. Okay. And there is nothing more to do at this point. G has no more edges. So G is the first vertex that actually got finished. So we have reviewed everything for G. So we come back. That pops up the stack and it returns to the call from DFS explore from I. So that finishes because there were no more edges. So I have to say that G is finished. I is finished. Then J is finished. Then L is finished. Then A is finished. Then H is finished. And then F is finished. J, L, okay? So what happened? We started from DFS explore from F and we visited every single vertex that is reachable from F. Okay? In the process, we found this is a tree. So you found F discovered H, H discovered K, K discovered L, L discovered J, J discovered I discovered G. So we have this is actually a path, but tree. And then we discovered these two edges. Okay, good. Now, the DFS explore has completed. Then we come back to this loop here. And we ask, oh, is there any more vertex not yet discovered? And the answer is yes. There are a whole bunch of vertices sitting here. Okay. So let's pick. So let's pick E. Okay. So we run DFS explore on E. So E has been now discovered at time 14. So we add E here. E has a bunch of edges. Let's say the first edge is E to F. Has F already been discovered? Yes. In fact, F has not only been discovered, it has also been finished. So this is the different kind of image. Okay? So let me mark it like this. Okay. So slightly different kind of an edge. All right. So we mark that like that. Then okay. So F has been already finished. So we don't explore that. So now E has edges to B, So it goes to edge B. Has B been discovered? No. So we move here, and this is the first time we are discovering B. So there is a squiggly edge here. From B, what do we see? There are two edges, 1 to D. So let's do D first. We add D here, and that's a D. From D, there is nothing to do. There are no edges out in D. So D is finished. Times the times 17. And you go back to B. Does B have any more edges? Yes, and that's the edge to C. So C is the first time you're knowing. So C has no more edges. So C gets finished. And we arrive back to B. Okay? Then does B have any more edges? Yes, it has an edge to E. Now E has been discovered but not yet finished. So this is of the same variety as this. Okay? Let me add another edge here. So that makes it very interesting. Let's say there is an edge from here to C. Okay? So let's say E now goes through this edge to C. What kind of edge? I should have. So sorry. So from B we are done, right? So from B we are done. B went to C and we are back. G. Now we are back to E. E has one more edge to do, and we go through that edge, and that's an edge to a vertex that has already been not only discovered but finished. So it's a little bit like this edge. Okay, then E is done. So E gets done at time 20, 21. And at this point, basically there is this DFS explore for E completes, and we come back here. Okay. Is there any vertex left to do? Yes. And that's the vertex A. So we start from A at 22.
Professor?
Yes.
How about E to G?
Thank you. Yeah, we should have checked E to G also. E to G is also an example where it's something to some from a vertex from E to some vertex that has already been done completely. Finished. Okay, so we come back to A. A has an edge to B to a vertex that has already been completed. This and gets done. Okay. So there is a reason for keeping track of all of this, but let me just. So if you look at the DFS traversal that we have just completed, the DFS traversal gives you the following forks. It keeps A separately because A has nothing that we didn't have any vertex that we reached from A. B was in the forest that was started from E. This is the tree that we had starting out of E. And then we had another tree starting out of H. So this is the DFS forest, depth first search forest, which consists of 3 trees. This is the trivial tree, empty tree. In this tree, E is the root of the tree, and these are all its descendants. In this tree, F is the root of the tree, and these are all its descendants. Yes?
Could you explain how you went about picking each root? The root,
Arbitrarily.
right? But couldn't that be dangerous because my DFS forest can look much different? than
Correct.
yours?
So it depends upon what you want to use it for. Okay. So for our purposes, the exact DFS forest won't be helpful. How things are organized in this will be the one that will be used. Okay. So we will see. You're absolutely right. I mean, in some sense, there is no one way to do DFS. Okay. But we will see that it has a lot of interesting properties which will enable us to look at the nature of these edges to make general determination about what the graph is without worrying about which order we selected the vertices. No matter which order we selected the vertices, we will have some good properties that come out. Okay. Okay. So, in this DFS traversal, these edges are referred to as tree edges. The squiggly edges are the tree edges. These are the edges that go from a parent to a child. Okay? Is that clear? Then we have edges such as this one. This is an example of an edge that is going from a descendant to an ancestor. Okay? This is an edge going from a descendant to an ancestor. Can you give another example of an edge from a descendant to an ancestor? G to J. Another example? B to E. Okay? So those edges are called back edges. They go from, this is parent to child, this is descendant to ancestor. Okay? Then we have these edges that I have marked like this. There are actually, these two are two different kinds of edges. Even though I just marked them like this because I marked them based on their finish time. And this edge, this edge E to F is going from one tree to another. You see, it's connecting two different trees. These edges are called cross edges. Okay. Basically, they go across trees. What about the edge from E to C? E to C is in the same tree, it's connecting two vertices in the same tree. But what kind of edge is it? From an ancestor to a descendant. And that's called a forward edge. Okay? If you're going from an ancestor to a descendant. So this is the cross edge, this is T to C. Okay? Alright. So the main value of DFS, as we will shortly see, is just being able to classify edges like this. Okay? And there are lots of benefits being able to do it. Let's try to, and these numberings are also very beneficial. Okay, the numberings that we have here. Okay. So here is, first, let's do the first question. Let's suppose I want to find out, and this is in a directed graph, I want to find out whether this graph has cycles. How can I tell? By doing the DFS and classifying all these edges or whatever. How do I tell under what situation will I get a cycle? If there is a back edge. Because remember, if you're starting, let's say, if you have, let's put that here. And this is where it doesn't matter how you run the DFS. Okay, so we'll prove this. So G has a cycle. This is a directed graph. If and only if any DFS has a package, finds a package. Can we try to argue this? Why is this the case? Okay, and I'm going to give a sort of a slightly informal proof here. Again, this is if and only if for both directions. Let's suppose G has a cycle. Okay? How do you prove that if G has a cycle, the DFS will classify an edges as a package?
The cycle will be in the same tree no matter what.
That is true. It has to be in the same tree, but
Can you pick one of the node in the cycle as the root, as,
well,
as the first one, and then you traverse down?
you're right.
And
But
at some point there will be a child.
very good. Except that I'm saying it doesn't matter how you run the DFS. You're absolutely right. If I were to pick one of the vertices in the cycle as a root and then I run it, okay, let's try to verify that. So let's suppose this we had a large graph, and let's say this was a cycle in that graph. And let's say this vertex is U. Then and there are some other edges. You don't know what's going on, but there are lots of other edges. Okay, but let's suppose we ran DFS starting from U. Then maybe we will visit other edges, but at some point before finishing this, we will visit this, right? Before finishing this, we will visit this. Before finishing this, we will visit this. Before finishing this, we will visit this. Okay, and then before finishing this, we will visit this. And then we will discover that, so this has to be a descendant of Q. If we haven't visited anything else before we start, right? So this must be a descendant of U. So there will be an edge one more descendant to an ancestor. So that will be a baggage. But there is no guarantee that we start our DFS from U. Right? We haven't specified the order. But what's going on is, if G has a cycle, let's look, our DFS is running. At some point, it hits the cycle. Let's look at the first time the DFS hits the cycle. The very first time. And let U be that vertex. Okay? So it must have hit from somewhere else, right? It must have come from somewhere else, because that's the first time we are doing the cycle. So suppose U is the first vertex discovered. Okay? By the nature of DFS, before U finishes, every single vertex would be discovered. You agree? Before U finishes. And it need not be in this order. You realize that, right? It might go like this. I don't know. There will be lots of ways it could but it will be clear that all of these would be its descendants. So in particular, this edge, when it's added, will be a okay. It may not match this cycle. So in this example, for example, this back edge might correspond to this cycle. It doesn't matter. There will be, it will discover this. Okay. On the other direction, if you find a back edge, then of course there will be a cycle, right? Because there is a path in the tree from the ancestor to the descendant, and now we have an edge going back, so there has to be a cycle. Path in DFS tree plus back edge implies this. Okay? So if you're a directed graph has a cycle if and only if there is a back edge. And so if you have to find out whether a graph is has cycles or not, you can run DFS and check whether there is a back edge. Okay? And a kind of graphs that have no cycles in a directed graph, they are called directed acyclic graphs. Okay? That's the definition. That's also sometimes referred to as a DAG. Directed graphs with no cycles. So how do you find out whether the directed graph has whether a graph is a DAG? Run DFS, check there are no back edges. Okay? So DAGs have very interesting and useful, even though they are a very special kind of graphs because there are no cycles, they have very interesting properties and are helpful in many settings. So the most canonical application of DAGs is that DAGs, if there are no cycles, they seem to capture precedence relationships. Okay? That if in order to do this, I need to do this before that. In order to do that, I need to do this before that. And in order to do that, so if you're doing a flow chart, flow charts might have cycles, but if you're running so you're trying to schedule a project in which you decide that this is the order of sequence of events, then you can put that into the project. So many projects processes with dependencies. Captured as okay. So when you're given a DAG, in situations like this, so I give you a sequence of tasks and I give you a precedence order between them, that before this task you have to execute this, before this task you have to execute this. It is very helpful to find what order should I execute the tasks so that I always maintain precedence order. That ordering is called topological sort or topological ordering. This is an ordering over the vertices of the DAG ordering over vertices of the DAG such that if I appears before j, or if u appears before j, vertex u appears before j, before b in the ordering, then there is no edge from b to u. Okay? No edge. Alternatively, all edges go sort of, if you're writing all the vertices in order, left to right, then all the edges have to go left to right. Okay? Alright, so let's take an example. So let's take so this has a cycle that goes like this. So let me fix this. Okay. So this is an example. So let's say A, B, C. Okay, so that graph is has no cycles, no directed cycles. Remember, in a directed graph, a cycle means it has to be directed. Okay, so there are no cycles in this graph, and we would like to find out. So, and let's say imagine these arrows being the following: that before I do G. Before I put G on in the task order or whatever it is, I must have done actually all the edges. I must have done C. Okay, so C has to be done before G. Before I do H, I must have done both F and G, and so on. Okay. So, what is the topological order for this? What is the order in which I should do the tasks?
Start with G.
Well, I cannot start with G. Before I do G, I have to have done C. Right. So start with A, and then we could do either. No, we have to do. We can't do B because before B we have to do D. So let's say C, and then you could do G. Yeah, I could, after G, you could do E. You could do E. You have to do D before E. So you have to do D. Then you can do E, and you can also do B, and then you can do F and then
F and F.
Okay. So this is the topological order. Okay. One thing to note here is if I write like this, all the edges go left to right. Okay? Okay, so how do I go about, given a DAG, we know that we can check whether the graph is a DAG by just running DFS and checking the original package. How do I find a topological order for a DAG? Okay. Well, you observe that A was the first vertex to try. So, how do you find out which is the first vertex to try? It has no edge coming in. You agree? Okay. So here is the topological sorted topological ordering for that. Find vertex B of G. Actually, while S with no incoming edge, what do you do? So you just add that to your list. Add S to topological order. Okay, you're keeping track of this. And then what do? Well, at this point what you could do is you could add A, and now that A is done, you can free up these edges. So you could just remove the edges going out of A, and just repeat. Remove edges out of S, and then you repeat. Is that clear? So you start from A. Then you remove these two edges. Then now you find these vertices that have no incoming edges are called sources. Source, okay? And edges that have no outgoing edges are called sinks. So you find the source vertex, remove these edges. Now what do? Find next source vertex. What is the source vertex here? C. Then you remove all of these edges, and you find the next source vertex, and you get G. Then you remove all of its edges, you find the next source vertex. There may be multiple source vertices. If there are multiple source vertices, it doesn't matter. Pick any one of the source vertices. Okay? Any questions? Yes?
What is the source vertex again?
A source vertex is the vertex that has no incoming edge.
Okay.
It has only edges going out. Okay, so it's a source. There is nothing coming in. A sink vertex is nothing going out. Okay. So notice that. Okay, so is this clear? So I'll say a couple of things. So why is there always a source vertex? Why should there be always a source vertex?
There's no cycle in it, so.
Okay, so what? There is no cycle in it, therefore it has to have a source vertex. Why is that?
Else, it will be two different graphs or two different trees once you don't have a common node or two.
Well, but let's say I just give you a directed graph, and I tell you it has no cycles. You have to prove to me that it must have a source vertex.
It becomes a tree and a tree and a boot.
It's not a tree because it's a directed graph. Notice that this graph is directed. It doesn't look like a tree. Yeah.
How could you disprove it though? Because doesn't it have to start somewhere?
Yes. No. Is this graph starting somewhere?
I mean, like any graph or tree would have to start.
This is not a tree.
No, I understand.
Yeah. So okay. So let me try to make a statement more precise. So G is a directed graph. It has no cycles. Prove that it has a source vertex. Is the question clear? G is a directed graph. I tell you it has no cycles, so it is a directed acyclic graph. Prove that it has a source vertex, a vertex that has no incoming edges. Yeah.
So, since it has no cycles, it means the absence of dark edges. So
Okay.
everything has to so a rational tree which is classification Grassland system.
Okay. So let's see. How do you prove that? So it's since G has, if you were to run a DFS, it will have no back edges. That's correct. But why does it mean that there will be a vertex that has no incoming edge? Yes.
I was just going to ask, are we assuming that it's a directed graph that's also a single connected or concurrent?
No. Not necessary. We haven't talked about what it means for a connected component in a directed graph, but yeah, there is no guarantee that there is a single. Somebody else has not. Yeah.
I mean, you could do a proof by contradiction. So, assuming it's a graph and it has all the vertices have like some kind of integrate, that means like each one of them has to fall from another vertex. So, if you do, so that means it has to like cycle around eventually.
Okay. So remember the proof that we did for trees and the undirected graph case. There was a proof for trees, the number of edges and so on. So here you could try to discover a cycle by doing, I look at any vertex, right? It has at least one incoming edge. So I go back on that edge. I go to a new vertex. It has it has at least one incoming edge. So I follow that. And I keep going. So this is true for every vertex, so I can't keep on going forever. There are only n vertices. So at some point I should come back. Oh, that would be a cycle. Is that clear? So I pick any vertex, so the proof is by contradiction. Pick any vertex. Pick any vertex. V. It has at least one incoming edge by, if it has no source vertex, then there must be at least one incoming edge. So you go back on that incoming edge. And if it has at least one incoming edge, that vertex, go back. That vertex, go back. At some point you will either, since there is only a finite number of vertices, you will back against one of the vertices, and that would be this. Next, because there are no source vertices, follow that edge. And repeat until each vertex already visited. That's the cycle. Yeah.
Aren't we proving the converse of what we want to prove and then saying that this is the converse?
Yeah, so the contradiction, what are we assuming? Let's assume it has no source vertex. Okay? If it has no source vertex, then we are going to show that it has a cycle. So that means if it has no cycles, it has to have a source vertex. Okay? So it's the proof is by contradiction. Assume there is no source vertex. Assume no source vertex. Then pick any vertex B. Since it's not a source, it must have an incoming edge. Follow that. That vertex is not a source, it must have an incoming edge. Follow that. Keep following it until you come back to one of the vertices that you've already visited before. And you'll have to do it because of the fact that there are only a finite number of vertices. Once you come back to a vertex that you've already visited, then that forms the cycle. Okay. Any questions about it? Okay. So, this algorithm is well defined. Otherwise, the algorithm is not even well defined, right? You can't run this on non-DAGs because non-DAGs may not have a vertex with no incoming edge. Okay. So why there is a vertex with no incoming edge? Add to list to move in. What is the running time of this? Okay. How do I find a vertex with no incoming edge? Well, we can simply go over the adjacency list and see which vertex has no incoming edge, right? And when you remove edges out of S, you can adjust your adjacency list, and if you, during that process, you find a vertex that has no incoming edge, then you add that to your list. So I will let you think about it. This can be implemented just in linear time. Very crucial thing to keep in mind that so far everything we have covered can be done just by manipulating the adjacency lists and keeping track of some things in lists, linked lists of some kind or the other. Okay? Okay, good. So far we have talked about depth first search and breadth first search for both undirected graphs and directed graphs. We have talked about directed acyclic graph, topological sort. Now let's talk about what it means for connectedness in a directed graph. Okay. In this graph, for example, you see that A can reach everybody. Can anybody reach A? Nobody. And it has to be the case, right? Because there's no cycles. If A can reach B, B better not be able to reach A. Okay. So what does that connectivity mean in a directed graph? So there's a very nice notion, and that notion is what's called strongly connected notion. Okay. So the nice thing about undirected graph was that the notion of connectivity is symmetric. If A is connected to B, B is connected to A. In a directed graph, clearly the notion of connectivity is not symmetric. So can we define a symmetric notion of connectivity? And the answer is yes. Let's say we define this notion of strongly connected. So I say that A is strongly connected to B. Okay? If you have paths in both directions, A has a path to B, B has a path to A. Okay, I'm drawing this picture to indicate that A has a path to B, and okay? All right. Now you agree that this is completely symmetric. This relationship is symmetric. It's also reflexive because A has a path to itself. It's also transitive. If A is strongly connected to B and B is strongly connected to C, then A will also be strongly connected to C. Okay? So this relationship is reflexive. That is, A is strongly connected to itself. It's symmetric. If A is strongly connected to B, then B is strongly connected to A. And it's transitive. If A is strongly connected to B, B is strongly connected to C, then A will also be strongly connected to C. So this is all, it has all the nice properties that you would like relationships to have. And so it forms what's called an equivalence relationship. Okay? So let's take a look at this graph. Okay? Does this graph have cycles? Yes, we had back edges, and so clearly we discovered cycles. So let's try to understand which vertices are strongly connected to whom. Okay? Is A strongly connected to anybody? No. So A is by itself all along. What about B? B. Okay. What about D? Is D strongly connected to anybody? So D is by itself. What about B? What are the other vertices that it is strongly connected to? Yeah.
Everything but A, C, and D.
So B. Yeah. So C is by itself. Everything but.
Oh no, I thought E and D were both.
Now E and B are connected to each other.
B, C will be a strongly connected.
Which one?
No.
Certainly B and E are the same strongly connected component. Everybody agrees. So B and E. Anybody else with B and E? No. Okay. What about F? What about H? K? So there is this big cycle. There is this cycle. There is this big cycle, right? This big cycle means all of these vertices can reach each other, right? So G, H, K, L, I, J, they are all together. Okay? What about F? F is by itself. Because, the reason is because none of G, H, I, J, K, L can reach F, and F cannot reach E. are the strongly connected components of the graph. People say this. It completely satisfies this definition. We haven't figured out how we calculate these. What is an algorithm to calculate this? But everybody sees that this works out. Okay. Let's try to look at some other interesting facts about it. So, what does this? So you notice that for this to be strongly connected, there has to be cycles in it. If there are no cycles, it cannot be strongly connected. So a strongly connected component has to have cycles inside. And just one cycle inside may not be enough. I mean, it depends upon how things are connected. So notice that there is a cycle here, there is a cycle here. Okay? Let's look at the other edges that are not inside, the edges that are going from one component to another component. Okay? Let's see. So here is an edge. Let me draw like this. That's from this component to this component. What about D? There is an edge from here to here. There is an edge from here to here. Notice that there are two edges. There is an edge from B, there is an edge from E. But I'm just drawing it as one from you can draw it. What about F? There is an edge from here to here. There is an edge from here. What about E? E has an edge. Okay? Is that clear? What do you notice about this picture? View each of these as just one node. Each of these rectangles as one node. So this is one node, this is one, this is one. So this is a graph over 1, 2, 3, 4, 5, 6 vertices. What do you notice about this graph of 6 vertices? It has no cycles. And it has to have no cycles. Why is that? Let's suppose I told you that there was a cycle between this, and this. Then they will be part of one strongly connected component. Because there is a way from one vertex from here to go here, there is a way for that vertex to go from here to here, the other vertex to go to here, then all of them are actually connected. Okay? So this is the very nice structure for directed graphs. You can decompose the directed graph into its strongly connected components, and the strongly connected components themselves form a DAG. Okay? So any directed graph G can be decomposed into its strongly connected components, SCCs, and the SCCs themselves form a DAG. This particular graph sometimes is referred to as GSCC. That's a helpful graph to keep in mind. Yes?
So the SCCs, so like all of the SCCs together form a DAG?
Yes. Where you're viewing each SCC, each connected component, to be one node, one mega node or meta node or something like that. Okay? Okay, good. So now the question is, how do we find these? How do we find the strongly connected components? And there is a beautiful algorithm for that. As such, let's say if time was not an issue, how would you go about finding a strongly connected components? There is a cycle. You just find out cycles. But let's say you have to come up with just the simplest method. I want to find out all vertices that are the same strongly connected component as A. How do you find that out? Yeah?
Find a path from A to any given node such that there's a path that goes back.
Correct. but let's say I want to find out I want to determine all the vertices that have that are in the same strongly connected component as A. So finding a path to a vertex that has a path back, it's unclear. How do I do that? Okay, I want to find out all the vertices. Let's break this down into two parts. I want to find out all the vertices that are reachable from A. How do you do that? I run a DFS from A. So if you do run a DFS from, so remember we had this DFS explore. I run DFS explore from A. When it ends, all the vertices that are ever reached are the ones that are reachable from A. You agree? I'm not running this part of the code. I'm just running this part of it. Agreed? Good. So I have a list of vertices that are reachable from A. Now I want to find out all the vertices that can reach A. What do I do? Run DFS for each other vertex, but can you do better than that? Well, here is a simple trick. How about I simply reverse the edges and run DFS from A? You guys agree with that? In order to find out all the vertices that can reach me, I simply reverse the edges and see all the vertices that I can reach. Because if it's a reverse graph, I can reach all the whatever vertices, then in the original graph, they can reach me. Okay? So that is a very useful routine, that is of reversing a graph. How do we reverse a graph? Well, it's straightforward. I have an adjacency list. If A had an entry for B, if A's entry had a B in there, then you go and put A in B's entry. It's just going through all the linked lists and then putting the right linked list there. Okay? So constructing the reverse of the graph takes linear time. Just go through all the edges and vertices. So if I needed to find so if my goal is to find strongly connected component of, let's say, vertex A of vertex B, what do? List all vertices. Okay, let's say L equal to list of all vertices reachable from A, reachable from B. Okay, how do I obtain that? I simply call DFS explore on B. And I get a list of all vertices reachable from B. And then I get, that's L1, let's say L2 is list of all vertices B can reach. How do I do that? I do DFS explore B in the reverse graph. Okay? Sorry, there's a second. That can reach B. Okay? DFS explore B, and then what do I return? The intersection of the two lists. Right? Vertices that can both reach V and can be reached. So I return. what will this give me? This will give me the strongly connected component for vertex V. It might be just that vertex itself. For example, if you run it on A in that graph, or it could be a bunch of vertices. Right? Okay. So this is how long does this take? Linear time. Because finding this takes linear time, this takes linear time, calculating reverse takes linear time, so that's just linear time. 3 linear times. But that only gives me the strongly connected component containing V. If I have to find out all the strongly connected components, what do? I do this for V, and I found some things. I won't touch them again. I'll pick another vertex and do that for that, and do that for that. But what will be the running time of that? Worst case, I might do it for A, then I might do it for D, then I might do it for C, and so on. So worst case, if I just do it for every vertex, repeat for vertices not listed yet to find all strongly connected components. Okay, so this running time would be worst case theta n times n. I'm going to write it as big O because I don't know whether it could be improved by doing something, but certainly we don't know whether it will take better than n times. Okay, but here is the very nice algorithm that actually computes strongly connected components in linear time. Okay, and it's a very clever idea, and so let's look at this picture there. Okay. The problem with this algorithm is, let's say I ran it from A. Okay. A can reach everybody. You agree? So from A you will go ahead and visit everybody, and then you will find after you come back that the only vertex that was part of A strongly connected component was A. So you spent all this linear time where actually you discovered a lot of things, but at the end you just gave A. Then we might run it on, let's say, B. From B you go ahead and visit all of the, remember if you do a DFS from B, you're going to go through all of these, right? So what would be better to do in this case?
If we run DFS on it.
So
in case we have a interlayer edge, then we can have a cycle average.
well, so from let's look at that picture there. So if I do a DFS from A, I visit the entire graph and then I come back and then I return just A. If I do the DFS from B, again I visit the entire graph and then I just say that B and E are together. What would have been a better, in what order should I have done it? What would be a better order to do? Instead of doing it at A and B, pardon? Start with something that is here. Let's say I run a DFS from here. Okay. Let's say I run DFS from any vertex here. What vertices will it visit? So DFS from H, what vertices will it visit? Exactly those vertices. And once you are done, what could you do? You could just set it aside. Okay, you don't even need to visit them. And then you could look at, then what could you do? You could do it on D or F. So which vertices, which groups are you picking? The ones that are sync. Okay? So here is the idea. What we want to do is Okay, now I'm going to write main idea, but find vertex B in the sink, in a sink node of this graph. Okay, I want to find a vertex in the sink node. Run DFS explore from that vertex B to find out to determine SCC of B. Remove these vertices and repeat. Remove these vertices and then you just do the same thing again. Of course, there is something weird about this algorithm. How do we know which vertex to pick in a sink node? That's exactly the. I wanted to find Simon canonical components. How do you tell me? So we're going to stop here, but here is the key point that you should remember. When you run DFS, no matter where you run DFS, no matter where you, let's look at that graph. No matter where you run DFS on that graph, which is the vertex that will be last completed on that graph? A. No matter where you run, no matter where you start from, the last vertex to complete DFS would be A. Why is that? Because A is a source. Right? Because A is in the source component. How do I find something in the sink? Well, you do the reverse. And you run DFS on the reverse first to discover a vertex that is in the sink. And okay, so I'm going to just add a sentence here and then we'll finish this next class. So instead of doing this, you do run DFS on okay? So this is the algorithm, except we only run the DFS once, and we go through this vertices in the order in which they finished last. Okay, I'll finish this next class. Oh, I do have a quizzes. I'm going to just leave the order. They are according to the last names. A and B, last name A. This is KB. Can you just keep it back? This is
Oh yeah, no, I like. They're like super practiced though. They know what they're doing. It's so scary. Like I don't know. All I could think about was like. All my friends could think about was like, wow, this is for real. Yeah, because it's not so real. Like it wasn't staged. They weren't actively trying to kill each other. As someone who rides horses, I'm always really amazed by how well trained the horses are. Because any of the horses I've ridden, if you tried to like joust on them, they'd throw you over the fence.
The horses I've ridden will throw you over a fence if like they feel like it.
Oh yeah, so like imagine what they would do if you were jousting on them. Man.
Motorcycles are dangerous. I feel like they're more than horses.
Horses are sweet though. So one of the first things they told me when I started riding was like one of the Oh, okay. I need to get over there.
What's your first name? Ruijin? Yeah.
This way.
It won't be like this for midterm.
Over here, I thought we would start.
Yeah, I think he's for himself. Until now it's 90. 准备到了是这个。准备那个给我。好，下一个，他这个给你太高了。就他不说拽热气的那个，不是拽的吗？拽的他死。我以前记得我5年前那上课的时候，他也掉了。拽。5年前的时候，没在那问，你刚才在问。羊屎。吓死我
L, right?
Yeah.
Last.
So, again. Yeah, actually,
Okay. Yeah. I think you can spin the
yeah. And then Sunday, pretty much. A lot of stuff like projector already knew. Yeah, you totally knew. I cooked it for everybody.
whatever you submitted, you was great.
Like omelets, like that. Whole chicken. Like go to the store, chicken.
Super towel.
You can almost call it figures.
不要好奇，要不好奇。
他会 take care of it.